Hi all, welcome to the sixth part of the video lecture on complexity theory. See, in the first five videos we covered in detail what is class P, NB, and then we saw that reduction, and in the last video lecture we saw that reduction from between two popular problems, independent set and click, and then after understanding what is reduction and how we can use one solution to one problem as a black box to solve another one, we formally define what is NB hard and then what about NB complete, like that. Now let's see something more about this reduction and the complexity classes. So let's start with the first problem, the conjunctive normal form satisfiability. So basically, Cook and Levin, as I already told you, they try to show that a particular problem circuit satisfiability or simply satisfiability in NP, and within that a special cases what is conjunctive normal form. Okay, so let me just say this is something not familiar for you, say SOP, POS, or in discrete mathematics you studied this terminology, normal form, conjunctive and distinctive normal form. So let me take a blank page and explain to you, then we will read that theory part. So basically one terminology we are interested is what is a literal. Okay, literal. So basically literal means any boolean variable or its negation. Okay, its negation. So take any variable, say P is a literal, Q is a literal, Q complement is a literal, R, like that. I can give any examples. Now another terminology is clause. What is a clause? So clause in the sense, so here again depending on the type of normal form we have SOP and POS, like that, in conjunctive or distinctive normal form. So here I am talking with respect to conjunctive normal form. Okay, so in conjunctive normal form basically we are having conjunction of clauses. So clause is basically disjunction of literals. Okay, disjunction of literals. Literal basically means variable or its negation, and clause is a disjunction of literals. For example, I can say P or Q. This is a clause. Okay, now P or Q or R complement. This is another clause. Q complement or R. So like that I can give any so I have a clause with the two literals here I have a clause with the three literals, here I have another clause with the two literals, like that I can define any clause. So basically the literal should be so we need this distinction operation between the literals. So distinction basically the or operation, right? Now what is CNF, conjunctive normal form? Basically what we are having is conjunction of, so conjunction of clauses. Okay, so clause is basically a distinction of literals. Similarly you can define something called a distinctive normal form, where the distinctive normal form is basically distinction of clauses where clause is conjunction of literals. Okay, so that also fine. So this is something equivalent to the product of sum that you studied in digital electronics. In discrete mathematics you may be familiar with the term conjunctive normal form. So product is basically product of some terms. So these or terms are basically the sum terms, right? And right, max terms, there you might use that term, and they are we are doing product operation between the clauses, or conjunction is basically product or and. So all these things are similar, but in different terminology, maybe in different domain, that's all. So this is basically conjunctive normal form. Now any boolean algebraic expression you can represent it using CNF as well as DNF, because these are two normal forms. And how any random boolean algebraic expression can be converted to this conjunctive normal form, repeatedly we use the distributive and associative law and grouping and all, we can do this. This is something you might have studied maybe or basically at least in digital you studied how we can come up with the product of some expression for any expression, right? Similarly SOP, maybe some methods you might know, or if you don't know you can refer that. Okay, so basically any boolean algebraic expression we can represent using this conjunctive normal form. And the problem we are interested is something known to be satisfiability. Okay, satisfiability problem. So what is satisfiability problem? Given any boolean algebraic expression, given any boolean expression, let me write like that, check whether it is is satisfiable or not. Satisfiable or not. So what is satisfiable? You know what is tautology? Contradiction, you know. Tautology means whatever be the combination of the input boolean variables, the expression is going to give you true. Always true. Always false is contradiction. Satisfiability is something that sits between a situation that is not just contradiction. Any situation other than contradiction is what you can call as satisfiable assignment, in the sense I just need at least one truth assignment such a way that the expression is giving you a true. That's all. So in the truth table, if you are getting at least one truth assignment for the Boolean expression, it is not contradiction, right? But I don't want a truth assignment for everything. If I am getting truth assignment everything, it is tautology. That is the extreme case of satisfiability. But I just want the expression to be satisfiable, in the sense at least one combination of the input Boolean variable, I should evaluate the expression as true. Okay, hope it is clear. Now if I have a Boolean circuit, some digital circuit, and I am asking the satisfiability question, whether this circuit is satisfiable, in the sense the circuit is having some inputs and output. Maybe you connected a bulb in the output of the circuit, and you are asking whether the bulb will turn on for any combination of the input, something like that. Okay, so we can call it as a circuit satisfiability problem. Now another, so the same circuit you can express just using a Boolean expression. Okay, so maybe a Boolean formula, and you can ask the same question, and now I can call it as a formula satisfiability problem. Now for any Boolean formula or Boolean expressions, basically you can convert that expression into conjunctive normal form, right? And if you are asking the same question, you can call it as CNF sat, okay, conjunctive normal form. So basically the underlying expression is in CNF form, that's all. Okay, now there are a more specific form of this conjunctive normal form. Say there are cases like 3 sat and all. Let me just introduce that. Now let me take an example. Suppose I have say n variables. N variables I am having. Let me write the variables as a1, a2, etc. an, and I want to form, I am having a Boolean algebraic expression, and the expression is in CNF form, and let me give the expression like this: a1, okay, and you know clauses you have to make, a1, a2, maybe complement, or a4. I'm randomly picking the variables, say, and conjunction of clauses, right? a1, a5, or a3 complement, something randomly I'm picking, okay, and a1, you can take a2 then, or a5, or a6, maybe here and there, so like that. So can you observe something here? So if you look at any clause, you can see 3 literals exactly, right? All clauses contain, see this word is important, exactly, I mean not less than or greater than exactly 3 literals, okay, literals. So such a formulation is what we can call as 3 conjunctive normal form. So basically conjunctive normal form with every clause is containing exactly 3 literals, and there are some speciality about it that we will see. So similarly, but in general, if you are looking at conjunctive normal form, there is no requirement like this. You can have clauses containing any number of variables random, and we are not restricting, and this is special case where we are restricting every clauses is supposed to contain 3 literals. Similarly, if all clauses contain exactly 2 variable, I can call it as 2 CNF, like that, okay. And for this kind of a Boolean expression, if I am asking whether this particular expression is satisfiable or not, we simply call this as 3 sat problem, okay. So this is basically 3 sat. 3 sat in the sense underlying conjunctive normal form, every clauses are going to contain 3 literals exactly. Normally this terminology is not so popular, I am calling like that. Basically the problem which people are which is mostly quoted in literature is 3 sat, okay. So now can you tell me what could be 2 sat? 2 sat, all clauses contain exactly 2 literals, right? Similarly, what is 4 sat, 5 sat, etc. Now why this is specifically interested is, the thing is that this problem 2 set, okay, is so first of all let me ask you in general, what about the difficulty level of this problem in general? I mean whether it is 2 sat, 3 sat, etc., or generally formula satisfiability. What about the what could be a solution that you think? Okay. So satisfiability problem, how can so let me just tell you that this is basically a difficult problem in the sense there is no polynomial algorithm available to check whether a given random expression is satisfiable or not. So can you tell me what is the brute force approach, the trivial brute force approach? I mean try all possibility, you know, I have n variable, and between this n variable I am making an expression maybe 3 set, but all n variables are involved, right? So the trivial approach says that for each variable try, I mean, you know, if I have a 3 variable, how many possibilities you have to check, right? Whether you are having a satisfiable assignment or not. The trivial approach says that say a1, a2, a3, I have a1 equal to true, a2 is equal to true, a3 is equal to true. That is one assessment. Then true, true, false, true, I mean true, false, true. Like that you can have 8 assignments possible, right? In the true table 8 entries will be there, and everything you have to check. And if at some point you are getting a truth assignment, you can stop. But in the worst case, suppose out of that 8, the first 7 may be evaluated to false, and the 8th one may be giving you a true. So that time the worst case running time goes to some 8 possibility checking when there are 3 variable. Actually basically what is happening is for the first variable I am getting 2 choice. It can be true or it can be false. Like that I am giving assignments, right? Similarly for the second variable again it can be true or false, and the third variable again it can be true or false. So what is basically happening? So there are 2 choices for the first variable, there are 2 choices for second variable. So totally how many, similarly for the third variable also independently 2 choices are there. So totally how many choices are there? 2 into 2 into 2 into product rule, right? Because the events are independent. In the sense, so product rule you have to apply, okay? Independent, dependent, so those probability notions you don't relate exactly. Anyway, I hope you got it. So there are totally 2 into 2 into 2 into 2, I mean 8 possibilities are there for 3 variable, but in general etc. for the last n variable also I'll be getting 2 choice. So totally how many possibilities I'll be getting? So I have n variable. For the first variable 2 possibility, second one 2 possibility, third one 2 etc., last one also. So totally there are 2 power n choices or truth assignments possible, and the worst case you have to check maybe 2 power n minus 1, that many combinations are giving you false, and the last one may be giving you true. Because of that the entire expression may be satisfiable. So the trivial approach is going to take some 2 power n running time, and this is something applicable to this 3 set also, because 3 set also basically it involves n variable, but only the structure matters. Every clause is going to contain 3 variable, like that. So that structure is having some relevance or importance that we might see later. But anyway, the problem inherently it is difficult, right? And as long as there is no easy algorithm, but as I already told you, these are all that confusion category. It's coming in between. There is no polynomial algorithm available for the time being, and at the same time in the future whether someone is able to come up with a polynomial solution or not, that we don't know also. So we classified them in that middle category, okay? So that about it. So there is no law, bound theory, proof, etc. Now 2 set also the running time is the brute force approach is going to take see for the 2 set also, if you are looking at the brute force approach, it is going to take 2 power n time only. 2 power n could be the complexity, right? But you know the specific why this 2 set 3 set are important, because 2 set is something polynomially solvable. There is a very okay, what I can tell, this is exponential running time, right? So we have a polynomial polynomial by default, I mean deterministic polynomial, okay? So don't confuse on that word. Deterministic polynomial time. So by default it is 2 power n, and the point is deterministic polynomial time algorithm exist or available. I mean, someone come up with such an algorithm for 2 set. Okay, so that is what we are interested, even though it looks like 2 power and like 3 set also, but still only for 2 set, available for 2 set only. Okay, there is no such algorithm available, and we can't even generalize or extend this 2 set solution to 3 set even. Okay, so 3 set, 4 set, etc., there is no easy solution available, but for 2 set it is available. So that is what we are interested, right? Okay, now I will just give you a hint like how this algorithm, this is basically this 2 set solution, and similarly in graph coloring we have a 2 coloring problem that also having a solution, and all these things are basically coming from what I can call a solution from, I mean, or using the depth first search algorithm that we studied in our graph theory. Those who are interested, this is something easy to understand algorithm. We can refer how this DFS can be used to solve this 2 set. Okay, similarly how DFS can be used to solve graph 2 colorability, bipartiteness, like that many applications are there, I say already told you. So here also we have a solution for this specific problem. And you know what is running time of DFS is this order of m plus n, right? If I have a so background, you know, this expression you will convert as a graph, or maybe how many variables are there that might corresponds to the vertices of the graph, something like this. Anyway, it is a polynomial, right? But 3 set and above there is no polynomial solution available. Okay, so this 3 set basically it belongs to class NP only. So belongs to class NP only, but the thing is 2 set belongs to class P. So this is something interesting. And a similar problem is maybe from a different domain. I don't know whether I can. Oh, I will just tell you 2 colorability is class P, and 3 colorability, 4 colorability, etc. that checking is class NP. So like that is the 2 and 3. There are many such interesting problems. Anyway, fine. So you got it right. So at this point, let me add you the next problem, that is from CNF to 3 CNF, and accordingly this 3 set problem. And this 3 set problem is something very important because most of the NB completers proof is basically starting from 3 set. So how we are reaching to 3 set? Basically we have a the satisfiability problem in general. I mean formula satisfiability or simply CNF satisfiability. Those things are already proved by a common framework given by Cook and Levin. And how that so these things are generally known to be the SAT problem. So it could be either formula circuit or CNF satisfiability. Particularly if the expression is containing clauses with exactly 3 literal, I can call it as a 3 set problem. And how this general satisfiability problem can be mapped to 3 set, I will give a just, I mean, basically any Boolean expression you have to convert into 3 CNF, that's all. So how we can do it, that I will explain now. And using 3 set, how we can solve other problem is what we are interested, and one such reduction is given in your syllabus also, that is click reduction, and that we will see maybe in the next video. So first we will see how any Boolean random Boolean expression can be mapped to this 3 CNF like that, and accordingly we can ask this 3 set. Okay, because that structure is something very peculiar, and that will help you to that can help many other problems. I mean this you can map to, I mean reduce to some other problem. So like that the 3 set structure is something specific. Maybe after understanding one problem you can follow it. Anyway, fine. And this is what I was trying to say from last few videos, that is Cook and Levin. What they done is they given a rigorous mathematical proof that says that the satisfiability problem is NP complete. And see, this is not there in your syllabus. You don't have to study the proof, and because it is somewhat hard to understand the problem. Maybe in the PG level you might study, okay, or if you those who are interested can spend time on it, but it is not something to be covered in a UG level. Okay, so this is something you can understand as a theorem, and you can trust that theorem. It is formally proved by 2 mathematicians or theoretical computer science, Cook and Levin, from 2 different parts of the world, and they done it, right? So most well-known Cook's proof using Turing machine characterization of the NB problem. So basically they convert they given a general framework using that Turing machine concept. As you already know, automata theory and algorithm concept, if you spend time on it you can understand the problem, but it is slightly difficult to follow. Okay, and So this is what happened basically. Even though it is something known to be Cook and Levin, the Cook showed that formula satisfiability is NB complete. This happened in 1971, and in the very next year there is I mean both of them together come up with mainly it is known to be Cook theorem. That's all. So Karp is another theoretical computer scientist or mathematician. In the very next year 1972 he got interested on the problem and he started showing many other problems are also NB complete, because we already got a framework, right? The starting point we got. So once you get the starting point, and you know from that point you can show others that I already told you. So many problems, how to do this reduction to the first problem is something done. This is the toughest task. So once it is done, from here to here showing some y's nb is straightforward, right? Maybe not so straightforward, but still if you spend some time on it, if you understand the how these two problems are related and how this reduction can be done, it is okay. Then similarly to z and similar to some say a, like that you can go to any problem. So like that some 21 problems are being reduced, being shown that NB complete by Karp in the very next year. So it is something known to be the Karp's very first 21 NB complete problem. So he did that reduction. So that also, if you are more interested, if you want to do your higher studies in this theoretical computer science, you can follow. You can try to spend time on it. So that's also here I just quickly tell you how any Boolean algebraic expression can be mapped to this reset. It's a very straightforward mapping. So basically, you know, given any Boolean algebraic expression, you can't expect this clauses are containing exactly 3 literal, right? And your intention is you want to make it 3 literal. So let me just take an example. So this is just containing only a single variable, and maybe so. This is another one, say containing a1 or a2 like that, and there is, so in between there should be conjunction a1. I am randomly taking a3 a4 or maybe a4 complement or a5. So this is okay, fine. And there may be another one maybe containing more than 3 literals also, say a1 or a2 a5 or a6 or a7, maybe let me give some complements also, fine. So something like that. So this is what you are having with you, and you want to convert this into some 3-sat formula. So basically the clauses with 1 or 2 literals, so first you have to expand these clauses to 3 literal case, right? So what you can do is replace every 2 literal clause by something like this, okay? So let me tell you how this can be mapped, and the same thing you have to generalize to one more level to this, okay? So what we are doing is, so we are just introducing some extra 2 variables. So if I have a clause with only 1 variable, you just introduce 2 more variable. If I have a clause with say 2 variable already, say x or y, like here a1 or a2, I am just introducing 1 more variable, okay? So and what I am doing is the same expression I am writing like a1 or a2 or, and this newly introduced variable, let me call it as some p, okay, because I don't want to use any name like from a1 to an, okay? So let me write like this, and this is something temporarily added to make the expression 3-sat, okay? So and what we are trying to say is the same a1 or a2 I am writing like this, a1 or a2 or q. Sorry, I am just introducing a single variable for or negation p, like that. So this will be nullified because you can simplify this expression. So what you can do is you can take this a1 or a2 outside, and what remains is a1 or a2. So when you simplify this expression, it will be something like a1 or a2 or p and negation b. And you know what is p and negation b? P and negation b is false, and something or false is that something. So this is basically a1 or a2 only, okay? I am not writing this part, hope you understand, right? So when you simplify this, you will get this back. So this kind of an adjustment you can do for a 2 variable expression. Now tell me how 1 variable expression clause you will handle. You just introduce 2 variable like this and write like this. That is straightforward, right? Write in the sense p or some this will expand to some 4 clauses further, okay? So that you write correctly, and this is fine, okay? And now what about this? When I have a expression with 4 variable, that you have to reduce. So for that again you can introduce some temporary variable like that. So I have an expression with some r variable I want to restrict to some t variable. Here I want to restrict to some 3 variables. So what I am doing is, so this one it's like a a1 or a a5 or a6, that particular part I am focusing. I mean, how many extra are there, that I will add in the next expression. Okay, so here I will introduce some temporary variable, let me call it as t, and now in the next expression I will start from negation t. Okay, so like this, negation t, t complement, and I will add the remaining terms. So here I have just a7 complement, this is a7 complement, right? So as the remaining one, so if I have a more, accordingly I will add. Now again, sorry, what happened here? So ultimately, so you can proceed in different ways. So here basically just take the first 2 variable only, like a1 or a5 complement, and at this point you just introduce this t. Now and t complement or a6 or a7, like that you can write. If this is further extended to more than 4 variable, now introduce another temporary and do that, and now you simplify this, you will get back to the original expression that you can see. Okay, so that's also this kind of an adjustment is basically what we are doing to convert any one second. And this kind of an adjustment is what we can do to convert any formula to 3 sets, so that now this reduction is something straightforward, right, and it's not going to take more than polynomial time. So I can say that any CNF satisfiability or in general satisfiability problem is polynomially reducible to 3 sets. So now you can take this 3 set as a starting point, and from that you can prove some other maybe random problem. So next video lecture we will see this is something coming from I mean digital electronics or discrete mathematics, right? Some based on some Boolean algebraic expression, we have this problem, satisfiability problem. Now we will relate it to something entirely different, say from a graph theoretic problem. We will see how this 3 set can be mapped to that click problem that we discussed in the last part. Okay, so like that different domains are being related to each other with this kind of a reduction, and it's something interesting if you are if you can spend more time on it. And few things that we are there in the syllabus only we are covering, and there are many reductions like this. Okay, so that that part we can see. So this is what we shown here, like 3 sat is NB complete. So first of all it is NB because there is no easy polynomial solution available, and also I mean non-deterministic polynomial you can proceed, but given any instance, what about the verification part, it should happen in polynomial time. So that is very important, because verification is something you just evaluate the expression using the truth assignment, that's all, right. So that you can do in polynomial time. And reduction 3 sat is important starting problem for many NB completeness proof, and that's why we shown that reduction. It is very straightforward, simple, direct mapping kind of thing, right. Next one is click, and how it can be solved in or how that reduction from 3 sat problem to click can be done, that we will see in the next video lecture. Yeah, thanks for watching.